Figure 4 shows a sketch of part of the curve C with the parametric equations x equals 3 theta sine theta, y equals sec cubed theta, where theta is between 0 and pi over 2. The point P with x coordinate k, y coordinate 8 lies on the C, where k is a constant. I need to find the exact value of k. K is the x coordinate of P. So in order for me to work that out, I would like to know what theta is at this point. If I can work out what theta is at this point, then I can substitute it into my x parametric equation to work out the x coordinate. And hence I'll know what k is. So how can I work out what theta is at point P? Well, at point P, I know that the y coordinate is 8. So I can say that sec cubed theta, which is my y parametric equation, equals 8. If I cube root both sides, I find that sec theta equals 2. Sec is the same thing as 1 over cos. So cos theta would equal a half. So theta equals cos inverse of a half, which is pi over 3. So I have just figured out that at point P, the theta parameter is pi over 3. I'm now going to substitute that into the x parametric equation to work out what the x coordinate is at that point. So 3 times pi over 3 times sine pi over 3. Well, the 3's cancel out here. So I get pi times sine pi over 3, which is root 3 over 2. So the x coordinate, and therefore the value of k, is pi root 3 over 2. And that's part A of this question done. Moving on to part B. We are given that the finite region R, shown shaded in figure 4, is bounded by the curve C, the y-axis, the x-axis, and the line x equals k. I need to show that the area of R can be expressed in this form. Right, to show that question, I need to show that this is true. Right, so let me start with the basic formula, which is that the area is equal to the integral of y dx, where I would usually have x limits. In this case here, however, we have got parametric equations. So actually, I want to integrate y times dx by dt with respect to dt, except it should be theta here, not t, in fact. And my limit should be in terms of theta as well. Right, well, I already know my upper limit in terms of theta. It's the pi over 3. We worked that out during part A of the question. Actually, let me do a new line here. So that's pi over 3. My lower limit of integration is whatever theta is here. Well, I know at this point here, I know x is 0 here. So if x is 0, then I've got 3 theta sine theta equals 0, which means that either 3 theta equals 0 or sine theta equals 0. And in both of those cases, theta will be 0. So that's my lower limit. Then my y function is sec cubed theta. Now I need my dx by d theta. So I need to differentiate the x with respect to theta. So let's do that here. if x equals 3 theta sine theta. Right, to do this, this is a product. So I need to use the product rule. So if I say u equals 3 theta and v equals sine theta, then u dash will be 3, v dash will be cos theta. So therefore, dx by d theta will be equal to u times v dash plus u dash times v. So that's my dx by d theta. So that's going to go in here. Right. I just need to show that this is the same thing as this now. Well, one thing I notice here is that I've got a sec cubed. They've just got a sec squared here and here. Let me just repeat that again. I've got a sec cubed. They've got a sec squared. So what I'm going to do is I'm going to actually split my sec cubed up into a sec squared theta times sec theta. And I'm even going to go one step further than that, because I'm going to remember what sec theta actually is. This sec theta here is the same thing as 1 over cos theta. And if I expand the brackets now, you can see why all of that was a good thing. So inside this bracket then I've got 1 over cos theta times 3 theta cos theta. So these coses are going to cancel out and just leave me with the 3 theta. And then I've got the 1 over cos theta times the 3 sine theta, where the sine theta over cos theta would become 3 tan theta. And now if I just expand these brackets, I get 3 theta sec squared theta plus 3 tan theta sec squared theta. We've got a 3 here, a 3 here, so I can take that 3 outside of the integral. And then that is exactly the form that we wanted it. So I've shown that lambda is 3, my alpha is 0, and my beta is pi over 3. Right, part C. Hence, use integration to find the exact value of the area of R. Now, there's a reason why they've told me to write it like this. So let's not worry about the 3 for the minute. Let's not worry about the theta sec squared either. Just focus on the tan sec squared there. That tan sec squared there is really easy to integrate. That's the reason why they've told us to write it in this form. Because tan times sec squared. If we are integrating just this, notice that sec squared is the derivative of tan. And therefore, I can ignore that completely, add 1 to the power of tan, and divide by the new power. This is a case where we're spotting a derivative, where if we can spot the situation where we have the derivative, times some function to a power, then we can ignore the derivative completely, add 1 to the power, and divide by the new power. That's what I've done here. Just to confirm that you are happy with that, let's differentiate my half tan squared and show that we do get back to that same tan x sec squared x. So if I were to differentiate this, I would first differentiate the outside function, which is the squared part. So I'd do 2 times a half, which is 1. I would take 1 away from the power, so the power would now be 1. And then I would have to multiply this by the derivative of the inside. The derivative of tan is sec squared. So we can see that when I differentiate this, I get this. Therefore, when I integrate the tan x sec squared x, I get a half tan squared. So we know the answer to this part already. Now we just need to deal with the theta sec squared. We need to think about what that's going to integrate to. Now, there's no spotting a derivative we can do here, but I can use integration by parts here, because when I differentiate this, it's going to become 1, and it will turn into a nice, easier integral to do. So I'm going to let u equal theta. I'm going to let v dash equal sec squared. So u dash will be 1. V will be tan. When I integrate the sec squared, I get tan. So let's apply the integration by parts formula, which is u times v, I'll write it down, minus u dash times v, the integral of that. So u times v, so theta tan theta, minus u dash, which is 1 times tan. And we can see now that that is going to be a much easier integral to do. Let me just do the 1 times tan theta is obviously just tan theta. Right. So we've got theta tan theta minus the integral of tan theta. Now the integral of tan theta, you have this on your formula booklet. It is ln sec. You do get given that on your formula book. So we have figured out that the integral of our theta sec squared is this, and our integral of our tan theta sec squared is this. So let's put both of those together now. So my answer is going to be 3 lots, because remember I've got that 3 on the outside of the integral, of theta tan theta minus ln sec theta plus a half tan squared theta. Now all I need to do is substitute my limits in. So let me just get a bit more space, and then we'll finish this problem off, because we're nearly there. And then we've got a nice 12 marks for this. So 3 lots. Let's substitute the pi over 3 in first. So pi over 3 instead of the theta minus ln sec. Now it's going to be quite difficult to substitute the sec, the pi over 3 into the sec, but I could think of this as being 1 over cos. And that's actually quite nice to do, because the 1 over, the ln 1 over this, I can just swap, because I can think of that as being cos to the power minus, cos pi over 3 to the power minus 1. And then with the laws of logarithm, I can take that -1 and put it at the front. So that simplifies my life a little bit. Plus 1/2 tan pi over 3 squared. Now I can substitute in the, so that's me substituting in the pi over 3. Now let's substitute the 0 in. Well, substituting 0 into theta at the front here will just become 0. So then I've got ln of cos 0 plus 1/2 of tan 0 squared. Right, so I've got pi over 3 times tan pi over 3. Now tan pi over 3 is root 3. Plus ln cos pi over 3 is 1/2. Then we've got 1/2 of tan pi over 3, which we know is root 3 squared, so 3. Cos 0 is 1. ln of 1 is 0. Tan 0 is 0. So 0 squared is 0. So everything else there is going to be 0. And finally, we can tidy this up then. So multiplying through by 3, that's going to cancel that. We'll have a 3 here, and that's going to be a 9 there now. And so my final answer is going to be pi root 3 plus 3 ln 1/2 plus 9 over 2. And actually, I could simplify that a tiny bit more, because ln 1/2 I know is minus ln 2. So let me rewrite that then. And so we'll have pi over 3 minus 3 ln 2 plus 9 over 2. And we're done.